All right, welcome. Today, we are diving headfirst into one of the most important rules in all of electricity, Ohm's law. Now, it sounds kind of formal, but it's really just a super simple relationship that, and I mean this literally, powers our entire world. By the end of this, you're going to see exactly what I mean.
But to really get a feel for this law, we've got to go back to the beginning. Back to its rather shocking discovery.
So, I want you to imagine something. You're a scientist. It's the early 1800s. You don't have any digital multimeters, no fancy sensors, nothing like that. How in the world would you even begin to measure how much electricity is flowing through a wire? Well, if your name was George Ohm, a German physicist, you couldn't just order something online. You had to get in the workshop and invent your own tools from scratch. He actually built his own incredibly sensitive equipment, things like galvanometers, just to get the precise measurements he needed. It was this obsession with precision, this dedication to getting it exactly right, that led him to his massive breakthrough. After who knows how many meticulous experiments with these homemade circuits, George Ohm finally uncovered the fundamental law that, of course, now carries his name.
So, what was this big secret he uncovered? It was a beautifully simple relationship between three key players. So let's meet our electric trio: voltage, current, and resistance.
First up to the plate is voltage. Now, the formal definition is the electrical potential difference between 2 points. But let's be honest, what does that actually mean for the rest of us?
The absolute best way to think about it is as the push. It's the pressure in the system. Think of a water pump pushing water through a pipe. That's what voltage does, but with electrons in a circuit. So more voltage just means more push. Next, we have current. This is the actual flow, how many electrons are moving. Now, you might be wondering, why the letter I for current and not C? It's a great piece of trivia, actually. It comes from an old French phrase, intensité du courant, which just means intensity of the current. So if we stick with our water analogy, if voltage is the pressure from the pump, then current is just the amount of water flowing through that pipe. It's the rate of the flow. And finally, that brings us to resistance. The name kind of gives it away, right? It's a measure of how much a material fights back or opposes that flow of electrons. It's the circuit's way of putting on the brakes. Back in our water pipe world, resistance is like pinching the hose. It's a narrowing in the pipe. The more you squeeze it, the harder it is for that water to get through. That opposition, that's resistance. So, we've got the push, which is voltage, we've got the flow, which is current, and we have the opposition, which is resistance. Ohm's true genius was figuring out how these three all relate to each other in a super simple, totally predictable way. And we can see it all with one single, powerful tool. And here's the elegant logic he discovered. Current is directly proportional to voltage. Basically, if you increase the push, you're going to increase the flow. Makes total sense. At the same time, it's inversely proportional to resistance. If you increase the opposition, you're going to decrease the flow. Simple as that.
And here's the best part. You don't need to memorize a bunch of different formulas to use this. All you need is this one simple triangle. You've got V up top with I and R at the bottom. This little guy is the key to the whole thing.
Check out how this works. Whatever you want to find, you just cover it with your finger. So you want to find voltage, cover up V, and look what's left. I times R. Need to know the current? Cover up I, and you get V divided by R. It is seriously that easy. Okay, so we've got the law down. Now let's take it out for a spin and see how it actually applies in the real world by looking at the two most common ways circuits are set up. So there are really two main flavors of circuits. Over on the left, you see a series circuit. Everything is connected in one single loop, one after another. But on the right, that's a parallel circuit, which gives the current multiple paths it can take. And this little table shows just how differently our electric trio behaves in each setup. In a series circuit, since there's only one path, the total resistance is easy. You just add up all the individual resistances. But in a parallel circuit, the current actually splits up between the different paths, while the voltage, that push, stays the same for every single branch. Getting these differences is absolutely key for designing pretty much any circuit. All right, you've seen the history, you get the concepts, you've got the magic triangle. I think it's time to put it all together. It's your turn. So here's a real-world problem for you. A simple hairdryer. It has 25 ohms of resistance, and you plug it into a standard 120-volt outlet. So using that little triangle, can you figure out how much current it's drawing? Go on, take a second. And there it is, 4.8 amps. To find the current, remember, you cover up the I on the triangle, which leaves you with V divided by R, so 120 volts divided by 25 ohms
gives us 4.8 amps. See? It's simple, it's powerful, and it's totally predictable.
So let's just quickly recap the most important takeaways. Voltage is the push, current is the flow, resistance is the opposition, and the incredibly simple formula, V equals I times R, is what describes their entire dance.
And that, my friends, is Ohm's law. It's so much more than just some equation in a textbook. It's a fundamental principle of balance in the universe. So the last question I'll leave you with is this. Now that you see it in electricity, where else in your world do you notice this same dynamic of push, flow, and opposition playing out? Thanks for tuning in.